Plants like this one spend millions of dollars every year to produce marketable, usable products. And just about all of these products will at some stage go through a process called distillation. It's a process based on the simple principle that different substances can be separated by their respective boiling points. In practice, however, this separation process can become quite complex as many different variables enter the picture. In this program, we'll review the basic principles of distillation and then focus on what you, the operator, can do to make the operation work more safely and efficiently. But let's start with the basics. The properties of various substances are determined to a large extent by the size and structure of their molecules. In distillation, the property we're most concerned with is boiling temperature. Substances composed of large, heavy molecules tend to boil at high temperatures, while smaller, lighter compounds have lower boiling points. Distillation uses heat to separate a mixture of different compounds by their respective boiling points, or boiling point ranges. Let's see how this works. When we add heat to this 50-50 mixture of butane and pentane, more of the light component, butane, boils off and goes into a vaporized state. If we cool and condense these vapors back to liquid, we get a fraction that is enriched in butane. The liquid that doesn't vaporize, on the other hand, forms a heavy fraction enriched in pentane. We can get an even cleaner separation by passing this mixture through a series of stills. The top stills operate at progressively lower temperatures, so less of the heavy component, pentane, is vaporized as we progress from one still to the next. This results in a relatively pure butane product being formed in the top still. The bottom stills operate at increasingly higher temperatures, so more of the light component, butane, is boiled out of the liquid as it is passed down to each lower still. This gives us a relatively pure pentane product out of the bottom still. This is essentially what happens inside a distillation column, except that the process continually repeats itself on each tray or in each section of the tower. Hot vapors rising up the tower heat the liquid on each tray. As a result of this exchange, light components in the liquid vaporize and heavy components in the vapor condense. This cycle gradually isolates a different fraction on each tray. The composition of each fraction is determined by the tray temperature. The lowest temperature occurs at the top of the column, where a cool liquid called reflux is returned, so a light fraction is formed here. The highest temperature is at the bottom of the column, where hot vapors are generated, so a heavy fraction develops in this part of the tower. Although there are many different types of distillation columns in any refinery or chemical plant, the goal of each is the same: to produce quality products that meet specifications at the lowest possible cost. Setting specifications for products allows us to control the type or range of molecules that are included in any one product. To determine product purity, we use boiling point tests or actually measure the percent of heavy and light key components in the product. Other specifications are set for flash point, API gravity or specific gravity, and color. Products are periodically tested to make sure that they are meeting specifications. When products are off specification, a change must be made in tower operations to bring the products back on spec. This is usually done by adjusting the heat and material balance inside the column. If we change the amount of heat that is put into or taken out of a distillation column, product's composition and quantity will also change. In most distillation columns, instruments are used to automatically control tower operations. Temperature, pressure, liquid level, and flow are the four primary variables that affect the heat and material balance inside a distillation column. Instruments function to keep these variables at a desired level or set point. Let's review how the distillation process works and how a tower is controlled to produce products that meet specifications. Stop the tape and turn to Workbook Period 1. During normal operations, control room instrumentation can automatically adjust to most changes in process conditions to keep the tower producing on-specification products. An operator is responsible for adjusting these instruments, collecting data, and making sure the tower operates at maximum efficiency. Distillation is a complicated process. In order to maximize production, a good operator must understand what happens inside a distillation column and why. When we say an operator should use logical thinking, we mean he should go through the following steps when working with a distillation column. The first thing he does is collect all relevant data on tower operating variables. Then he analyzes this data to determine if there is an operating problem. If so, he considers all the different ways it can be corrected, chooses the best solution, and makes the necessary adjustment. Finally, he checks the results of his action to make sure the problem has been resolved. Suppose lab tests show an overhead product has an end point 15 degrees higher than called for by specifications. An operator quickly increases the reflux rate to remove heavy material from the overhead product. In this situation, has the operator used logical thinking and made the correct adjustment? No. The operator in this example did not check all the data on the tower operating variables before increasing the reflux rate. This chart shows that the current tower operating conditions have not changed from the previous readings. Had the operator analyzed this data, he might have suspected that the endpoint test was inaccurate because none of the tower operating variables had changed. The most logical thing to do in this situation would be to retest the overhead product before increasing the reflux rate. During the normal operation of a distillation column, there is a certain set of procedures that an operator should follow. Let's go over these control procedures and then apply them to some normal operating situations that an operator is likely to encounter. An operator is usually responsible for sampling or testing distillation products at regular time intervals. He also checks instrument readings at the same time these samples are taken. On some distillation columns, process analyzers automatically monitor product specifications. These test results and instrument readings are recorded in the unit logbook and are then compared with previously logged instrument readings and test results. If the test results indicate a product is not meeting specifications or an operating variable has changed, it may be necessary to adjust the tower operation. But before making any adjustments, consider the possibility that the tests may be inaccurate, or that an instrument or automatic controller is malfunctioning, or that there is some other mechanical problem. The data should fit together. If the total picture of the operating conditions seems unreasonable, you should question whether the data shows the actual state of tower conditions. Suppose instrument readings tell you that the flow of steam to the reboiler has increased and that the temperature at the bottom of the column has decreased. Other tower variables remain the same. Does this data fit together? If you answered no, you are correct. An increase in the flow of steam to the reboiler should result in an increase in temperature at the bottom of the tower. The reading of the steam flow rates or the tower bottom temperature may be wrong. Another possibility is that the reboiler itself is not operating properly. When it is necessary to change tower operations, always make the change that will bring the product back on specification with the least effect on other tower conditions and with energy efficiency in mind. These adjustments should always be made gradually. Sudden changes will cause a tower to behave erratically, reducing fractionating efficiency. A distillation column does not respond immediately to operational changes. When we adjust the heat balance inside a column, there is a gradual change in product composition. This chart summarizes what happens when we increase the reflux rate to remove butane from an overhead product. You can see that it takes 50 minutes to reduce the butane content in the top product from 11% to 6%. The amount of time needed for a tower to adjust to operational changes will vary from column to column. When making cut point changes, always give the tower time to adjust to these changes. Then take new tests and instrument readings to see if the product is meeting specifications. Let's look at another situation. In this column, the end point for the overhead product has increased from 100 degrees Fahrenheit to 105 degrees Fahrenheit. You know that heavy molecules boil at high temperatures, so the new end point indicates the overhead product contains material that is too heavy. Looking at the instrument readings for this same column, you can see that tower top temperature is the only variable that has changed. An increase in the amount of heavy material on the top trays is responsible for the temperature increase. Before correcting the operation, logically think through the problem. One way to remove heavy material from the top product is to increase the reflux rate. Another way is to decrease the reboiler temperature. In this example, you would probably decrease the reboiler temperature because of the energy savings. However, increasing the reflux rate may be the quickest way to remove heavy material from the overhead product. Let's review the control procedures that are used during the normal operation of a distillation column and work through some more problems. Stop the tape and turn to section 2 of your workbook. During the normal operation of a distillation column, an operator makes minor adjustments to the heat and material balance to keep the column producing on-specification products. These adjustments are fairly routine, so when a tower is operating normally or at steady state, it is relatively easy to control. An operator is faced with a greater challenge when a tower is operating abnormally. There may be several different reasons for this, so an operator must develop troubleshooting skills to identify these types of problems. One abnormal operating situation is flooded trays. When a group of trays in a distillation column become completely filled with liquid, the tower is said to be flooded. Too much liquid flowing down the tower can result in flooding. When the capacity of the downcomers and trays is exceeded, liquid backs up in the tower and the column floods. A vapor rate that is too high can also cause flooding. The pressure from excessive vapor rates resists the flow of liquid down the tower. If this pressure is high enough, liquid will back up the tower and flooding occurs. For vapor to move up a tower, there must be a difference in pressure between the bottom and top of the column. In a tower that is operating normally, the highest pressure occurs at the bottom and then gradually decreases as you move towards the top. This differential pressure is the driving force that pushes vapors up through risers and bubble caps and through the liquid that is on each tray. The driving force that moves liquid down a column is called hydrostatic head. This is simply the depth of liquid that exists in the downcomer. The higher the head, the greater the downward force. To travel down a tower, a liquid must overcome the resistance caused by the upward pressure of the vapors as well as friction in the downcomers. In a tower that is operating normally, the differential pressure of the vapors and the hydrostatic head of the liquid are in balance, and there is a steady two-way flow of fluids through each of the trays in the column. Excessive vapor or liquid rates through any one of the trays can upset this balance for the entire column. The diagram on the right shows what happens when either vapor or liquid rates are increased, holding other operating conditions constant. You can see that this causes the hydrostatic head of the liquid to increase, which can lead to flooding. There are several ways to identify a tower with flooded trays. First, you will find that there is very little temperature difference or gradient across the flooded section. This occurs because the composition of the liquid is essentially the same on all the flooded trays. Second, a tower with flooded trays produces poor quality products. This is due to poor vapor-liquid contact in the flooded area, which reduces fractionating efficiency. Third, in a flooded section of a tower, rising vapors have to push against a very high hydrostatic head of liquid. As a result, differential pressure in this area of the column is larger than normal. And fourth, the pressure tends to fluctuate inside a tower that is flooded. This is because the vapors underneath the flooded section must build up a very high pressure before they can overcome the resistance of the liquid. When the vapors reach this pressure, they suddenly blow through the liquid and pressure below the flooded section quickly falls. This build-up and blow-through cycle is what causes pressure to fluctuate in a flooded tower. High liquid levels sometimes occur in the bottom of a distillation column because too much liquid is entering the tower or not enough bottom product is being removed. A tower with a high liquid level exhibits the same characteristics as a tower with flooded trays. There is very little temperature gradient from tray to tray. Fractionating efficiency decreases. Differential pressure is larger than normal, and pressure throughout the column fluctuates. Another abnormal operating situation is dry trays. Dry trays sometimes occur because too much liquid is drawn off as side product. When this happens, the trays in a section of the tower immediately below the draw-off point become dry. An interruption in the supply of reflux or insufficient reflux to cool the rising vapors can also cause dry trays. Reflux problems are usually responsible for dry trays at the top of a distillation column. Dry trays will also occur if the feed or reboiler temperature is too high. The high temperatures produce an excessive amount of hot vapors. These vapors boil away all the liquid on the trays directly above the feed or reboiler inlets. You can identify a tower with dry trays by the following characteristics. First, the tower will produce poor quality products because no fractionation can occur on a tray without liquid. Second, the temperature on a series of trays without liquid will be about the same, so the temperature gradient in this section of the tower is very reduced. And third, there will be a small differential pressure through a series of dry trays because there is no liquid to resist the flow of vapors. Abnormal operations can also be caused by water that inadvertently enters the system. The water may come in with the feed or accidentally through a pump line and gets trapped in an area of the tower where the temperature is below the boiling point of water. Most hydrocarbon streams are lighter than water, so they float on top of it. When a section of trays becomes filled with trapped water, fractionation in this part of the tower stops because there are no hydrocarbons to make contact with the upward rising vapors. Since water is a relatively pure compound, trays with trapped water will exhibit very little temperature difference or gradient. When trapped water vaporizes to steam, it can pose a grave safety hazard because it expands 1,600 times in volume. Sudden vaporization of water causes pressure surges that can damage internal tower hardware and, in extreme cases, can even rupture a tower. Another condition that can interfere with normal operations is upset or damaged trays. Upset trays are usually caused by excessive vapor velocities, by the sudden vaporization of water, or by liquid surges in the bottom of the tower. Upset trays do not fractionate properly because vapors are not forced to bubble through the liquid on the trays. As a result, the liquid on a series of upset trays will have the same composition and will exhibit little temperature difference. Since it is easier for vapors to flow around upset trays than through bubble caps, a tower with upset trays will usually exhibit a decrease in differential pressure. A tower will also operate abnormally if the cooling medium to a condenser is lost. When this happens, the amount of heat that can be removed from a tower is greatly reduced. The condenser will immediately start to overheat and may be damaged unless the heat input to the tower is quickly reduced. When there is not enough cooling water or air going to the condenser, tower top temperature and pressure will suddenly increase. The loss of the cooling medium will cause the liquid level in the accumulator to decrease because hot vapors can no longer be condensed to liquid. A higher temperature also means that heavier material is driven up the tower, so the overhead product becomes heavier. A less severe but more common problem with overhead systems is fouling or scaling of condenser tubes. Deposits in the condenser tubes interfere with flow through the vessel and decrease the effectiveness of heat transfer from one fluid to another. Another situation that will cause a tower to operate abnormally is the loss of the heating medium to heat exchangers and reboilers, or the loss of fuel supply to furnaces. When the heat supply for a column is cut off, temperature and pressure inside the tower will quickly start to decrease. Less heat means that fewer vapors will be formed, so the liquid level in the bottom of the column will increase, and the bottom product gets lighter. Instruments and/or alarms will usually identify which piece of equipment has malfunctioned. Fouling or scaling is a common problem in furnaces, reboilers, and heat exchangers. As with a condenser, these deposits restrict flow through a vessel and reduce heat transfer efficiency. Solid deposits can collect and plug screens, valves, and pipes that serve as outlets from a distillation column. Plugged outlets seriously restrict the amount of product that can be drawn from a tower, and they must be cleared if the column is to operate normally. The problems that occur in vacuum distillation columns frequently relate to the system's ability to maintain an adequate vacuum. Vacuum columns operate at very low pressures to reduce the amount of heat needed to separate the feedstock. In many towers, the vacuum is maintained by passing high-pressure steam through a series of ejectors. The movement of the steam pulls non-condensable gases out of the system. After passing through the ejectors, the steam is condensed to water and collected in a vessel called a hot well. A loss of vacuum in a vacuum distillation column is usually caused by one of the following problems: improper steam pressure to ejectors, hot well flooding, the presence of too many non-condensable gases, loss of cooling water to condensers, or erosion or blockage of steam ejectors. Let's review the conditions that can cause a tower to operate abnormally and consider the solutions for each of these abnormal operating problems. Stop the tape and turn to Workbook Period 3. One of the marks of a good operator is the ability to analyze various operating problems and control a tower that is operating abnormally. Abnormal operations present an operator with many different variables and alternate solutions. The operator must identify the problem, determine the cause, and then implement a solution that will bring the column back to normal operation. When dealing with a tower that is operating abnormally, an operator should follow the same orderly pattern of thought that is used to control a tower during normal operations. The first thing an operator does is collect all data on current test results and instrument readings. Next, the operator compares current test results and instrument readings with previous data so he can correctly identify the problem. For any given problem, such as flooding, there may be several different causes. So in addition to identifying the problem, an operator must also determine what is causing it. Then the operator chooses the best way to solve the problem and makes an adjustment in tower operations to correct it. After an adjustment is made, an operator continually monitors instrument readings to make sure the situation is not getting worse. The tower is given time to adjust to the operating changes, and then new tests are run to see if the products are back on specification. You should always be skeptical about tests and instruments. A situation that seems abnormal may only appear so because of faulty instruments or test results. Double-check instrument readings and test results before making changes in tower operations. One of the difficulties of abnormal operations is that an operator often has a limited amount of time to discover the cause of a problem and remedy it. Some situations, like a rapid increase in tower pressure, require quick action. Other situations, like a gradual loss of cooling water, can be approached and corrected more methodically. An operator should estimate the time he has available to correct a problem and then work within those time constraints while implementing a solution. When working with a tower that is operating abnormally, you should have several alternate solutions. In the event that your first action does not solve the problem, you will be able to make a second adjustment without delay. In choosing a course of action, never compromise the safety of personnel or equipment. Always think through the consequences of any action you might take before making an actual change in tower operations. If this action risks the safety of personnel or equipment, choose another solution. Let's work through a hypothetical problem. This chart gives the data for a tower that is operating abnormally. The temperature gradient between the feed zone and the tower bottom has decreased from 200 degrees Fahrenheit to 50 degrees Fahrenheit. Specifications call for a bottom product with an initial boiling point of 400 degrees Fahrenheit. The IBP is down to 180 degrees Fahrenheit. Differential pressure between the feed zone and the bottom of the tower has increased from 10 pounds to 14. And finally, the tower bottom level is high. After collecting the data, your next task is to identify the problem. A decrease in temperature gradient and impaired product quality are found in all abnormal situations. An increase in differential pressure is found only in flooded trays and high levels, so one of these two conditions is probably causing the problem. Since the decrease in temperature gradient is at the bottom of the column and the bottom level is high, you would assume the problem is due to high levels. You know that high levels are caused by either too much liquid entering the tower or not enough liquid being taken out. A check of the feed and reflux rates shows that these variables have not changed value. So the problem is probably not caused by too much liquid entering the column. Checking the flow leaving the tower, you find that the bottom product flow rate has decreased. The reduction in the bottom flow rate appears to be responsible for the high level. There are several conditions that could result in not enough liquid leaving the bottom of the tower. One possibility is malfunctioning instruments. A check of the control valve on the bottom product outlet line shows that this valve is wide open. Instruments do not appear to be causing the problem. Another possibility is a faulty pump. A pump check shows that it is working, but the pump has an erratic discharge pressure. You decide that the pump is causing the problem. In this situation, you would immediately switch to a standby pump to reduce the high level. The bad pump can either be repaired or replaced. Let's work through some more hypothetical problems dealing with abnormal operations. Stop the tape now and turn to Workbook Period 4. Because the components in most liquid mixtures boil at different temperatures, we can usually separate these mixtures by normal distillation. But when the components have the same or nearly the same boiling points, separation by normal distillation can be difficult, and in some cases may even be impossible. In these instances, it is necessary to use another type of distillation to bring about a separation. One distillation method that can separate substances with very close boiling points is called extractive distillation. In extractive distillation, a third component, usually a solvent, is added at the top of the column. As the solvent moves down the tower, it attaches itself to one of the components in the feed and carries it to the bottom of the tower. The component not absorbed by the solvent, in this case product A, is removed at the top of the tower. The solvent and product B are removed at the bottom of the column and are then sent to a second tower for separation. The second tower, called a solvent recovery column, separates the absorbed component from the solvent by normal distillation. The product is taken off the top of this column and the solvent is recycled back to the first column to continue the separation process. The solvent used in extractive distillation has a boiling point that is considerably higher than either of the components being separated. Since it is heavier than both products, it falls to the bottom of the extractive column without being vaporized. The wide boiling point difference between the solvent and the component it absorbs allows us to separate this mixture by normal distillation. Some substances cannot be separated by normal distillation because they form a constant boiling point mixture when they are brought together. These constant boiling point mixtures are called azeotropes. Azeotropes can boil at a temperature that is higher or lower than the boiling points of the components that combine to form them. Water, a byproduct in many petrochemical operations, and isopropyl alcohol form an azeotrope that boils at 165 degrees Fahrenheit. In this case, the boiling point of the azeotrope is lower than the individual boiling points of either of the two components. Note the composition of the azeotrope. It contains 88% alcohol and 12% water. If we attempt to separate water and isopropyl alcohol by normal distillation, the water not contained by the azeotrope will fall to the bottom of the column. The water moves downward because it has the highest boiling point. The product produced at the top of the column is the azeotrope because it has the lowest boiling point temperature. Since the azeotrope goes overhead, it is impossible to produce a dry alcohol product in this tower. In order to obtain a pure isopropyl alcohol product, the azeotropic mixture from the first column is sent to a second tower. In this example, a solvent is added to the system. The solvent joins with the other two components to form a three-way or ternary azeotrope. The major function of the solvent is to absorb all of the water that comes into the tower. The ternary azeotrope has a lower boiling point than the two-component azeotrope that entered the column, so it goes overhead. Since all of the water is in the ternary azeotrope, a dry isopropyl alcohol product can be removed at the bottom of this tower. When the ternary azeotrope is condensed overhead, it forms two different liquid phases. The liquid phase that is rich in the solvent is recycled back to the azeotropic column. The other liquid phase contains mostly water along with some isopropyl alcohol. This phase is routed back to the first column. Let's review the principles of extractive and azeotropic distillation and look at how some other products are separated using these methods. Stop the tape and turn to Workbook Period 5. Distillation columns are periodically shut down for routine maintenance and inspection. In this section of the program, we'll take a look at some general procedures that are used during shutdown and startup operations. An operator should always read the specific shutdown and startup instructions for his unit before such operations. These procedures will vary from tower to tower and from plant to plant. The first step in most planned shutdown operations is to gradually reduce the feed rate into the column. As we reduce the amount of material put in the tower, the product output also decreases. By making gradual feed rate changes, the tower instrumentation can maintain the design conditions inside the column. This allows us to produce on-specification products while the feed rate is being reduced. The feed rate is reduced until the tower is on total reflux. At this point, no feed is being added to the column and no products are being withdrawn. The material that remains in the tower continues to fractionate, but is not removed as product. The next step is to gradually reduce the heat input to the tower. In vacuum columns, the vacuum is taken off and the column is shut down under atmospheric conditions. As the temperature in the tower decreases, light components fall to the bottom of the column and mix with the heavier material. This liquid mixture is pumped out and saved for reprocessing. Because pressure decreases as temperature is reduced, there's always the possibility of a vacuum occurring in the tower while it is being shut down. If a vacuum occurs in a tower that is not designed for vacuum operations, the column could collapse. To prevent this from happening, an inert gas like nitrogen is introduced into the tower to maintain a positive pressure. After the tower has been shut down, drained, and pumped out, It must be cleaned of all hydrocarbons or other organic or chemical material. This is because these substances can form potentially explosive mixtures when their vapors combine with air. For a mixture to be explosive, the percentage of vapor in air must come within certain limits. This chart shows the explosive range of some hydrocarbons when mixed with air. For example, when an atmosphere contains between 5.3% and 14% methane, it forms an explosive mixture. Because it is difficult to tell precisely when a mixture of air and hydrocarbon vapor reaches the explosive range, it is best to completely avoid mixing hydrocarbon vapors with air. In shutdown operations, all hydrocarbons are taken out of the tower before any air is let in. And during startup, all the air is taken out of the tower before hydrocarbons are introduced into the column. One way to remove hydrocarbons from a tower is to purge the column with an inert gas like steam or nitrogen. Inert gases can strip or displace hydrocarbons off metal surfaces inside the tower and move these vapors out of the column. Water can also be used to clean out a tower. Some columns are flushed out with water and the liquid containing hydrocarbons is drained out the bottom. Other towers are completely flooded with water. The flooding operation floats hydrocarbons to the top of the column where they are removed. In some instances, a combination of water and steam is used to clean out the tower. If a tower is completely flooded with water, there will be no gas or oil left in the column. In order to drain the water, we vent the tower to the atmosphere. This prevents a vacuum from occurring above the liquid level while allowing the liquid to flow out the bottom. When a column is vented to the atmosphere, there is a possibility that hydrocarbon vapors from other parts of the unit will enter the tower and form an explosive mixture. To prevent this from happening, metal plates or blinds are placed in all tower inlet and outlet lines. Blinding a tower effectively isolates it from hydrocarbons that are present in other parts of the system. Purging with inert gases and water flooding or flushing should remove all hydrocarbons from the tower. But we can't assume the tower is safe until it is actually tested. There are several different types of hydrocarbon detectors and analyzers that can detect the presence of hydrocarbons. Before anyone enters a tower, it must be tested with one of these devices. After the column is purged and tested for hydrocarbons, one of the manways is opened and an air mover is turned on. The air mover can be a fan or an air eductor like the one shown here. In the event that any hydrocarbon vapors are released during the cleaning of the tower, the air mover will sweep these vapors out of the tower. Cleaning of the tower should be thorough and complete. Even after purging and water flooding, there are usually some stubborn deposits that remained in the column. These deposits are removed with special solvents or by manual scraping. After the tower has been thoroughly cleaned, it must be carefully checked for corrosion. We do this to make sure that all equipment is still strong enough for future use. A corrosion inspection is usually made by measuring and recording the thickness of various metal parts inside the column. While the tower is open for repairs, the vapor and liquid paths should be inspected to make sure they are free of obstructions. Downcomers and bubble caps should be free of solid deposits. Even a partial blockage of a vapor or liquid path will cause inefficient tower operation. A list of scheduled repairs is normally compiled prior to shutdown. Any other problems that are discovered during the inspection of the tower are then added to this list. By keeping thorough written records, we make sure no necessary repairs are overlooked. After all repairs are made, the tower is given a final check to see that no tools, equipment, or clothing have been accidentally left in the column. A foreign object could plug an outlet after the tower is back on stream, making it necessary to once again shut down the process. After everything is checked and the tower is closed, all air in the column must be removed. This can be done by adding an inert gas like nitrogen or steam to the tower. An oxygen analyzer is then used to verify that no air remains in the system. All blinds installed during the shutdown process must be removed prior to startup. Before the tower is brought back on stream, it is necessary to perform a tightness test to make sure there are no leaks in the column or in the connecting equipment. A tightness test is usually performed by running pressurized steam or nitrogen into the tower. A pressure buildup indicates there are no leaks. If the pressure continually bleeds off, there is a leak somewhere in the system. After the tower is tested for leaks, the inert gas or steam pressure is released. A hydrocarbon vapor is then backed into the column to avoid pulling a vacuum. Before starting the tower, make sure that all auxiliary equipment like reboilers and condensers are ready for operation. Also, make sure that any water that might have settled in low points has been drained out. The procedures for the actual tower startup will vary from column to column. You should always follow the guidelines for your particular tower. Remember to make gradual increases in temperature and pressure when starting up a column. Rapid temperature and pressure changes can stress and damage equipment. Let's break from the video now and review the control procedures that are followed during startup and shutdown operations. Stop the tape and turn to Workbook Period 6. Computer control of distillation processes has become increasingly popular in recent years. The ability of computers to quickly and accurately control tower operations makes it likely that they will be used in even greater numbers in the future. Basically, a computer is a device that stores data and performs calculations. It is programmed with a number of mathematical equations, which it uses to determine the ideal operating conditions for a tower. Let's take a look at how the system works. Information about a process variable is measured by traditional measuring instruments and is sent to the computer by process transmitters. The computer converts this data into mathematical calculations to determine if the process is operating at maximum efficiency. Based on the outcome of these calculations, the computer either sends a signal to position a control valve or signals a controller to position the valve. In some systems, the computer performs the necessary calculations, and an operator makes the actual adjustment on the controller. From this brief discussion, you can see that the computer occupies a position similar to the controller in conventional instrumentation. It receives and analyzes measurement information about a process variable. Then it provides an output signal that is used directly or indirectly to position a control valve. The computer, however, has many features that distinguish it from a typical controller. For example, a computer has a memory which allows us to store vast quantities of information about the process being controlled. This information can easily be reviewed for troubleshooting purposes or for checking historical trends in the values of specific variables. The computer has a very large capacity and can operate at very high speeds. Where a separate controller is needed for each control loop in conventional instrumentation, a single computer can operate the control loops for an entire plant. In a computerized control system, process data is displayed on a CRT console. These consoles organize and display process data in a variety of easy-to-read, logical formats. In most systems, an operator can call up video displays ranging from a broad overview of the entire process plant to a detailed analysis of a single control loop. The majority of the computer systems on the market are equipped with alarm displays. These displays automatically flash to warn an operator about any abnormal operating situation. Other displays that can be shown on CRT consoles include checklists, flowcharts, and full-color schematics of process equipment. Any of these displays can be called up instantly with a touch of the finger. This quick and orderly display of information makes it easier for an operator to understand the dynamics of the process and gives him more time to devote to controlling the operation. A keyboard attached to the video console is the interface between the operator and the process. Set point adjustments and requests for display information are made by pressing the appropriate keys on the board. Many computer systems are equipped with printers that provide written records about the condition of variables being controlled. The ultimate justification for using the computer is based on economics. Results from plants and refineries that have switched to computer control indicate considerable savings in the areas of energy conservation, throughput capacity, and recovery of valuable components. Let's take a look at how computer control can improve the operational efficiency of a distillation column. Measurement data on process variables is continuously fed into the computer's memory. The computer uses this data to calculate the actual liquid and vapor flow rates inside the tower. This information on internal liquid and vapor rates, along with data on other relevant variables, allows the computer to accurately predict the composition of products before they are actually produced. The computer continuously compares its product's composition estimates with the current operating conditions to determine if ideal conditions are being maintained in the tower. Based on this comparison, the computer adjusts tower variables so that the products will meet specifications but not greatly exceed them. This saves energy and maximizes capacity. If there is a change in the condition of a process variable, like reflux temperature, the computer immediately calculates how this change will affect product composition. The computer can then adjust the tower operation to keep the column producing on-specification products at the lowest possible cost. Most computers rely on product composition analyzers to verify the accuracy of their predictions. The most common composition analyzer is the gas chromatograph. A gas chromatograph can analyze the composition of a product stream, just as the plant laboratory would, in as little as 30 seconds. This information is fed into the computer's memory to trim and adjust computer calculations and the output signals that are sent to control valves. A computer, assisted by on-stream process analyzers, is often used to control a chain of distillation columns. When working with a group of towers, a control strategy that considers the entire chain as well as the individual towers is needed. This is because products often have specifications limiting the amount of both heavy and light impurities. Let's consider an example. The overhead product in this depropanizer is propane. Specifications will allow up to 3% ethane in the overhead product. Can the amount of ethane in the propane product be controlled by the depropanizer? If you answered no, you are correct. The only way to keep ethane out of the propane product is to limit the amount of ethane that leaves the deethanizer. Ethane has a lower boiling point than propane. So all of the ethane entering the depropanizer will rise to the top of this column and become part of the propane product. When an operator is controlling a series of towers with conventional instrumentation, he must balance out the specification requirements for a number of different products. In some instances, he may have to temporarily relax specifications on one product to avoid changing the composition of a more valuable product. During a process upset, it becomes especially difficult to maintain product specifications because an operator has to simultaneously make adjustments to several towers. More effective control of a series of towers is realized by using chromatograph analyzers in conjunction with a computer. During normal operations, a computer-based system makes closer cut point divisions than conventional instrumentation. This saves energy and allows us to recover more of the valuable components. During process upsets, the computer quickly gathers and analyzes all the important data. The computer then advises the operator what operational changes to make, or makes the changes automatically. These adjustments keep the entire series of towers operating at maximum efficiency until the problem is resolved. Let's break now and consider how a computer-based system can improve the operation of a multi-product distillation column. Stop the tape and turn to Workbook Period 7. In this program, we have reviewed the basic principles that cover how distillation works. In a distillation column, hot rising vapors contact a cooler descending liquid on a series of trays. As a result of this contact, light components in the liquid vaporize and heavy components in the vapor condense. This cycle gradually isolates a different fraction on each tray whose composition is determined by the tray temperature at a given pressure. Since the lowest temperature occurs at the top of the column, a light fraction is formed here. A heavy fraction is isolated at the bottom of the tower where the temperature is highest. An operator's primary job is to control the distillation process so that the products produced will meet specifications. While most process variables are controlled automatically by control loop instruments, it is the operator who is responsible for adjusting these instruments so that they accomplish the job they are designed to do. During normal operations, an operator usually makes minor adjustments to the heats and material balance to keep the tower producing on-specification products. Most of these cut point changes are made by adjusting the reboiler or furnace temperature or by changing the reflux rates. Product rates are then adjusted to maintain the desired material balance. An operator is faced with a greater challenge when a tower is operating abnormally. In these instances, a person must use troubleshooting skills to identify the problem and determine the cause. In this program, we introduced you to extractive and azeotropic distillation processes, two special types of distillation that are used to separate components with the same or nearly the same boiling points. We also outlined some general control procedures that are followed during shutdown and startup operations. And we included a basic introduction to computer control of distillation processes. In addition to making an operator's job less complex, computer control saves energy, increases capacity, and allows us to produce more of the valuable components. This concludes our second program on distillation. Thank you for watching.